In this video, I'll go through the Kruskal Wallis test, which is a non-parametric alternative to analysis of variance. So in this example, we have 3 colleges, and we have performance evaluation ratings for employees from each of the colleges. And these are the ratings here. And what we've done is we've ranked the ratings. So the rating of 15 is the lowest rating, and that has the rank 1. And then 20 is the next lowest, and has rank 2. This one's rank 3, and so on. And then there's a couple of ties. So there's 2 employees with ratings of 80, and they're tied with an average ranking of 15.5, and so on. Okay, so there's our data. So our analysis, we have 7 from College A with a rank sum of 95. So that's just the sum of the ranks for all the employees from College A. 6 from College B with a rank sum of 27, and then 7 from College C with a rank sum of 88. So right away we can see that College B has lower rankings than the other 2 colleges. So the employees there are getting lower ratings on average. The total sample size is 20. We're going to use that when we calculate our test statistic. So our hypotheses here is the null hypothesis is that the populations are identical from all 3 colleges, and then the alternative is that the populations are not identical, or they're not all identical anyway. You can frame this test as a test of the medians instead if you assume that the population distributions are the same, and then the null would be that the population medians are all the same, and the alternative would be that they're not all the same. So what we do is we calculate this test statistic here, which we're going to call H, and it has a fairly horrendous formula, but it's easily calculated just using all the numbers that we just calculated. So the sample sizes and then the rank sums. So you put them all together and out pops this number, 8.92 for the value of the test statistic. And then we can compare that with a chi-square distribution with 2 degrees of freedom, 2 because we have 3 different colleges, and the degrees of freedom is 3 minus 1, which comes to 2. So we use the chi-square distribution, and we look in the right tail for the p-value. So to the right of 8.92 is a p-value of 0.0116. Compare that with our significance level to find out whether to reject or not reject the null. And because 0.0116 is smaller than 0.05, we reject the null hypothesis. So there's evidence that not all the populations are the same here. And we noticed that when we looked at the data, that the ratings for College B seem to be a bit lower than the other 2. We could also use a critical value here. That should say chi-squared critical value, not F. There we go. And that comes from a chi-square distribution with 2 degrees of freedom. With a tail area of 0.05, we get 5.991. And you look at the test statistic, see if it's in the rejection region beyond 5.991, and it is. So same conclusion, reject the null hypothesis. So let's use Excel stat here and see what it comes up with. So non-parametric test and comparison of K samples, Kruskal Wallis. So Excel stat calculates the test statistic a little bit differently, but it's reasonably close to the way that we did it. So and then the p-value is pretty close too. So the data is the ratings, And then the sample identifiers are the colleges. The data is set up as one column per variable. So I selected this, and then Kruskal Wallis is what we'll do. And then under options, we'll do an asymptotic p-value using the chi-square distribution. And we'll OK that. And so it calculated a test statistic of 8.984, reasonably close to what we got. P-value is pretty close to 0.0112 is what they got. Same conclusion. Let's make this a little bigger so you can see. There we go. So there's the p-value, and the conclusion's the same. Computed p-value is lower than the significance level, so you should reject the null hypothesis in favor of the alternative, and the alternative is that the populations are different. So that's the Kruskal Wallis test, which is an alternative, a non-parametric alternative to analysis of variance.